Good day, viewers. I trust you've had an amazing day. Welcome to another edition of Gassing It Out with Laughing Gas. Right, let's jump into this topic, a very interesting topic at that. For some of you that are lovers of physics, welcome on board. Go get your pen, go get your book, add calculator, join, because the topic we want to see is a very interesting one. Unit and dimension. And then we are going to be looking, first of all, at fundamental and derived quantities. Fundamental quantities are quantities that are original. They were not derived from anywhere. Derived quantities, on the other hand, are a combination of two or more fundamental quantities. I'm going to do a rundown of the fundamental quantities, their units, and their dimension. So we have the fundamental quantities, and then the units, and then the dimension. So let's see how many we have. Okay, the first on our list we have length, and the unit of length, the standard unit of length is meters. The dimension of length is capital L. The next one is mass. The unit of mass is kilogram, and the dimension of mass is capital M. And then the next one is time. The unit of time is second, and the dimension of time is capital T. The first one is current, and then the unit of current is amperes. The dimension of current is I. We also have voltage, and then the unit of voltage is volts, and then the dimension is still V. And then the sixth, we have temperature. The unit of temperature is Kelvin, and then the dimension is theta. And then we have number of moles or amount of moles. You have the unit is in mole, and then the dimension is N. And finally we have luminous intensity. And then the unit is candela, and then capital C is used to denote the dimension. Alright? However, there are many other fundamental quantities, but we are restricted because of the undergraduates. In undergraduate, this one will do. Alright, so let us see derived quantities. Now, unlike fundamental quantities, derived quantities are a combination of two or more fundamental quantities, like I said in the opening remark. So, example is area. Area, you know that area is length times breadth. So that's two length. That's our unit is going to be meters squared because of length times breadth, and the dimension is L squared. We also have volume. Volume is length times breadth times height. That's actually three dimensions of length. That's meters cubed. The dimension is L cubed. And then we have density. You know the formula for density? The formula for density is mass over volume. Since it's mass over volume, the unit will be kilogram per meter cube. Kilogram per meter cube. That makes the dimension. We are working with the dimensions depending on what we have from the units. That's M, capital M, coming from the mass, and then per meter cube, the meters. You remember that the dimension for meters is length, so per liters cube. We now have velocity. Velocity is distance all over time, so the unit is meters per second. So what becomes the dimension? The dimension is liters, that's L, capital L, then per T, L per T. We have acceleration. Acceleration is definitely velocity over time, that's meters per second squared, and so the dimension will be L per T squared. L per T squared. We have force. Force is mass times acceleration. So the unit is newtons. We all know the generic unit of force is newtons. But if you are breaking it down so that we can furnish the dimension, it is actually kilogram meters per second squared. This is actually Newton. The entire scope of this unit is newtons. So that is M, because of the kilogram here, that's for mass. Meters, that's L per T squared. And so it's actually simple. We now also have pressure. Pressure is actually force all over area. Force over area. So just take, for instance, we have force, that's the unit of force, kilogram meters per second squared, divided by the unit of area, which is meter squared. So what are we going to have? You see that this meters is going to cancel one of the meters there. So by the time we sum this up, we now have kilogram per meter per second squared. So if we are furnishing the dimension, we have M per L per T squared. Okay? And then we have other dimensions and quantities such as impulse. Impulse is simply force times time. Ft, force times time. And impulse can also double for momentum. So whatever unit we get from impulse is the same thing we will get for momentum. So that is kilogram meters per second squared multiplied by seconds. That's for the time. We'll end up having kilogram meters per second. So that is to say our dimension for impulse will now be M L T inverse. So that will be the dimension for impulse. And finally, we have surface tension. Surface tension. Remember that surface tension is the force that acts perpendicularly to the surface of a liquid. So that's, in a short form, surface tension is simply force per unit length. So that is to say, kilogram meters per second squared divided by meters. So meters cancels meters. We'll now have that the dimension is definitely meters, or M per second squared. That's M per T squared. So these are just but a few dimensions that are derived, their units, and then the dimension for the derived quantity. So we are going to see how we use this thing to derive mathematical relation. Because one of the advantages or merits of derived quantities is that it helps to provide the physical quantities, the relationship between physical quantities. Alright, okay, so let us look at an interesting problem. Let me tell you, problem is what makes physics sweet. Look up. Yes, I'm talking to you. Look up. Problem 1. Remember, I've given you fundamental quantities. I've given you derived quantities. I listed the quantities. I listed the units. I listed the dimensions. Knowing the dimension is one part. Knowing how to apply them is another part. Now, look at a particular interesting question. The velocity V. What do you notice? Velocity. Anytime you want to answer physics question, please endeavor to take note of the parameters given. The velocity V of a transverse wave in a string depends on tension T. Tension T. In the string, its length L and mass M. So it means that velocity depends on tension. The velocity also depends on the mass. So they now said, use the method of the dimension analysis to obtain the expression for velocity. So that's, we are going to now x-ray all these parameters in their dimensional form. So look at this. So we have velocity depending on tension and also depending on the length and also depending on the mass. So that is to say, by the time I let go of this proportionality sign and introduce my equal sign, I'll have V to be equal to K T L M. Alright? K T L M. So that is to say, I'm now going to write out all the dimensions. I'm going to write out all the dimensions Remember that the dimension for velocity we gave earlier on is LT inverse, okay? LT inverse. So in order to make this thing easy, I can decide to introduce alphabets X, Y, and Z. So we now have K into tension. Another name for tension is actually force. So tension is also a force. So remember that the dimension for force is MLT inverse or MLT raised to the power minus 2. Then remember that the power is X. Length is still length because the dimension for length is still capital L raised to the power of Y. And the dimension for mass is capital M raised to the power of Z. So let us play out with these numbers or alphabets and see what it gives us. So minus 1 equal to K. Now we use this power to open this bracket. We have M raised to the power of X, L raised to the power of X, and T raised to minus 2X. You can see I use this X to open the bracket, and then I write down my Y, Ly, and then M to the power of Z. So the next thing I'm going to do, remember what I want to discover is to identify the value of X, the value of Y, and the value of Z. These are the indices that will give me useful information in providing the relationship between these physical parameters. So I'm going to compare the power of L. Compare the power of L because L is actually the first alphabet we have here. So by the time we compare the power of L, look at, initially speaking, the power of L here is 1 to be equal to whatever, where we have L here, we also have L here. So we have L is raised to the power of X here, plus L is also raised to the power of Y. So this becomes my equation 1. So I'm now going to compare the power of T. So I'm going to compare the power of T because T is the next alphabet and term there. So by the time I compare the power of T, so remember T here is raised to the power of negative 1. So I have negative 1 is equal to, we have only one T here. So negative 1 is equal to the power of negative 2. So that is minus 2x. Because the power of T here at our right hand side is minus 2x. While the power of T here at our left hand side is minus 1. So automatically I'm going to make x subject of the formula. Minus sign cancels minus sign. I have 1 to be equal to 2x. If I make x subject formula, I have to divide through by 2. And then I'm left with x is equal to 1 over 2 or half. Remember, in my equation 1, we've already established from equation 1, we already established that 1 is equal to x plus y. So in order for me to find the value of y, I'm going to substitute the value of x into this equation. So I'm now going to have 1 is equal to 1 over 2 plus y. So instead of putting x, I have 1 over 2. If I move 1 over 2 to the other side of the equation, we now have 1 minus 1 over 2 to be equal to y. So this means that y is equal to 1 over 2. Now we have gotten the value of x, we have gotten the value of y. So to get the value of z, I now equate, compare the power of z, compare the power of m in order to find z. Now if you check our equation, our main equation, there is no term for m here. So if there is no term on our left hand side for m, it actually means that it's 0 to be equal to, we have two terms for m here, m raised to the power of x and m raised to the power of z. So I'm going to have x plus z. So we've already established that x is half. So it means that 0 is equal to half plus z. By the time I make z subject formula, when this half crosses, I'll now have that z is equal to negative half. So remember, I've gotten the value of my x, I've gotten the value of my y, I've gotten the value of my z. So my x, let me reiterate, is 1 over 2, my y is 1 over 2, and my z is negative 1 over 2. So if I will now answer this question, it means that velocity is actually equal to k, which is a constant, into t raised to the power 1 over 2 instead of x, and then L instead of y, 1 over 2, and then M, which is the mass, raised to the power minus 1 over 2. You can see I have substituted the values of x, y, and z. So in a nutshell, in mathematics, anything that is raised to the power of half is just another expression for square root. So V is equal to K, then I'll put my root sign, and then TL. You can see that M is raised to the power of negative half, so it's actually a denominator. So you can decide to end your answer this way, but remember that the length over M, that's length per unit mass, is actually equal to a single term here, mu. So I can actually say, instead of having L over M, I can decide to substitute the value of mu into this equation, so which actually gives me V is equal to K into my tension. Instead of L over M, remember L over M is mu, you now put your mu. So this is actually the working relationship. You can see how fundamental and derived quantities has helped me to, establish a relationship between these parameters: velocity, tension, length, and mass. Let's see 2 other examples. All right, let's see another problem. Fantastic problem. For physicians or physicists, give them problem. That's how they grow. For what values of x, y, z, and gamma is the expression m raised to the power of x, l raised to the power y, t raised to the power z, and theta raised to the power gamma is Boyle's law, Charles' law, general gas law, and density. So what we are asking us to do is use the knowledge you've gathered in dimension analysis to derive the expression for Boyle's law and check and compare it to this expression. Now, first and foremost, what is Boyle's law? Boyle's law states that the volume of a fixed mass of gas is inversely proportional to the pressure applied, provided that temperature is held constant. So that means this at constant temperature. So that means if I remove this proportionality sign, I'll have V is equal to K over P, volume pressure. So it means that the constant K is equal to volume times pressure. So the only thing now is for me to write out the dimension. Remember, do you recall that the dimension for volume is actually LQ, and then the dimension for pressure is ML raised to the power minus 1, and then T raised to the power minus 2. So that means I'm just going to arrange it to look like our parent's expression here. So it means that the constant for the Boyle's law is m raised to the power minus 1. Since I have 2 L's here, I'll compress it, 3 minus 1 raised to the power 3 minus 1, and then T minus 2. So finally, I'll have m raised to the power minus 1, L, 3 minus 1 is 2, and then T raised to the power minus 2. So it means for Boyle's law, my value of A, look at x, y, z, and gamma. So if you check, x is the power of m. So it means that here x is minus 1, and then y is 2, and z is minus 2. Since there is no term in theta, it actually means that gamma is 0. So for Boyle's law, x is minus 1, y is 2, z is minus 2, and gamma is 0. Let's check for Charles' law. Charles' law is not difficult. Charles' law. Remember that Charles' law states that the volume of a fixed mass of gas is directly proportional to the absolute temperature. So it means that V is directly proportional to the temperature. So if I remove the proportionality sign, I'll have V equal to KT, making the constant subject formula will have K to be equal to V over T. The next thing is I'll start inputting the dimension. The dimension for volume is LQ, and then the dimension for temperature is theta. So by the time this one comes up, it means that K is equal to L cubed theta negative 1. That's theta inverse. So automatically, there is no term in M and there is no term in T. So that means that for Charles' law, X is 0 since there is no term in M, and Y is 3, and then Z is 0 since there is no term in T, and then gamma is minus 1. So that's as simple as that. Let's see the last two. The general gas law. General gas law is just the combination of Boyle's and Charles' law. That is PV over T. I usually do this. By the time you cover this is Boyle's law, and then by the time you cover pressure, this is Charles' law. The combination of the Boyle's and the Charles law gives you the general gas law. So we go straight to impute the dimensions. The dimension for pressure is mL inverse T raised to power minus 2 multiplied by the dimension of volume, which is L cubed, divided by the dimension for temperature, which is theta. So K is actually, by the time I combine these two, I'll have M and then L raised to power minus 1, T raised to power minus 2, L raised to power 3, and then theta raised to power minus 1. So since I have two terms of L here, by the time I compress, I have, this is M, L raised to power 2, T raised to power minus 2, and then theta raised to power minus 1. So it actually means that my K is equal to mL squared T raised to power minus 2 theta minus 1. So for general gas law, the value of X is 1, the value of L, which is Y, is 2, the value of Z is minus 2, and then the value of gamma is minus 1. So finally, we now go straight to the density. The formula for density is actually mass over volume, mass per volume. So we now fix the dimension. The dimension for mass is capital M. The dimension for volume is little L cubed. So we now have M raised to power minus 3. So automatically, the term in X, the power of M here is 1. So X is 1. Y is negative 3. There is no term in T, so Z is 0. And there is no term in theta. It means that gamma is also 0. So this is actually how you can breeze this through. Okay? Sorry, this one, not negative 1, and then this 1. So it means that for Boyle's law, X is 1, and then Y is 2, Z is minus 2, gamma is 0. So what is going to happen now is I'm going to give you a giveaway question. What you do is just drop your answer at the comment section. The most active participants that will share, subscribe, like will definitely get a fantastic package from me. All you have to do is just DM me, comment on the comment section, post your answers there, and then you get my package. So see you at the comment section. Okay, here goes the giveaway question. If the gravitational force F is given by this relation, F is equal to capital G, you know that the capital G is the gravitational constant, the universal gravitational constant, multiplied by M, both of them are mass, that's two bodies, divided by the radius. Of course, you know that radius is measured in meters. I'm giving you S already. So if you fail this question, you have me to contend. Derive the dimension of the universal constant, G. Alright, so all you need to do is just to find G, make G subject formula, and that's it. So I want to actually thank you for staying true to the end. Thank you for making sure that this word goes viral as possible by way of you sharing, by way of you liking, by way of you commenting. We want to get engagement. And then please do well to endeavor, whether regardless of the fact you are a science student, you are science-based or not, you have siblings, you have friends that are science-based. You can do well to share, like, let them see this video. This is just an academic video that will help them to study. It's a study guide. So please, we are asking that you share, you like, you comment, and then turn up your notification bell so that as soon as we upload a new video, you will be the first to get it.